Now, for training purposes, we put fuel delivery at the end. Of course, you would start here if you're going to check for fuel delivery problems, and it's a good place to start for misfire. And when you start here, start with fuel pressure and volume test. We're going to do voltage and current testing of the fuel delivery system to help answer questions that simple fuel pressure and volume tests may overlook. It's going to be slightly more advanced than what most people do for their fuel ignition system. We're going to do a fuel pump current test. Now, there's a number of people that swear by volume test for a pump, but the only really good volume test we've seen that work is one where you check the full volume at the pump. We found that fuel pump current can yield a great deal of information. And we're going to do injector voltage test. But we found some problems that injector voltage alone would miss, so we have an injector current test. We're going to do it well. Let's start back at the beginning. You must start with a good specifications. Key on, engine off, good place to start. Compare it to specifications. Once the engine's running, does it still meet the same specifications? Pay attention and remember that sitting here in the service bay at idle is not the most difficult time to deliver fuel. There may be other operating modes. In fact, I guarantee you there are other operating modes that are far more difficult for fuel delivery to be held at a steady pressure than here. But be aware that low pressure readings may be caused by a bad regulator or a low pump output, and in a few rare cases dirty fuel filters. But we know most of the time it's the regulator that's bad. High pressure can be caused by a bad regulator or a crushed return line on those systems that don't have a returnless system. So be careful and check the return line if it's too high. What's going to be wrong with it being too high? You're going to get too much fuel delivery. Fuel trim will be very negative. You have too much fuel. We're trying to tie all this together for you. We keep trying. I hope you appreciate that. Now, the volume test, if you want to do it, you do it with the engine running, and if you do it the Schrader valve, you open the Schrader valve and allow gas to flow into an approved container. Now, there's hard specifications for volume like this are hard to come by. But a good general rule is there must be at least 1 pint of fuel in 30 seconds. And high-performance vehicles should have about 1 pint in 15 seconds. However, be warned, we have seen vehicles that pass this test but still can't deliver fuel at wide open throttle. That's why we get so excited about things like the wideband air-fuel ratio sensor, so we can check fuel delivery at wide open throttle. Low volume, number 1 cause, dirty fuel filter. Number 2 cause, low fuel pump. This number is reversed itself recently because now we're finding it more fuel pumps than we are fuel filters. But if we go back 10 years, there were more dirty fuel filters than pumps. Now the numbers seem to have switched around. Measuring fuel flow at the tank outlet is the most accurate way to measure volume. You're going to have a very large volume, and to get that, you're going to have good pump output. Now let's talk about that pump output for a minute. We've got a low amps probe down here you're looking at on the left. We're going to use a lab scope in this low amps probe that we simply clamp around a wire to look at current going to the fuel pump. It's an alternative way of testing for fuel volume. You say, how can that be? Well, a pump must have normal current flow to deliver full fuel volume. Now that sounds very simplistic, but it's not. It's beyond simplicity. If you can't get enough power to the pump, it can't deliver full fuel flow. The pump motor can only give you full output when it has full power. So one of the statements we can make that's just as positive is that fuel pumps with low current cannot deliver full fuel volume. That's a very big finding. It seems so basic, yet it's very, very important. We're going to show you how we're going to measure. But before we get there, let's talk about what's going on in the fuel pump. If this fuel pump has good power and good grounds, what else has to be making good contact for it to get full current? Well, we've taken and chopped off one of these rotors. They normally come in from the end, and we've taken these two brushes and show you how to make contact. The one on the left, the brush is in contact with two different parts of this segments of the rotor, the commutator. We have decreasing current on one and increasing current on the other. If we're going clockwise, we're decreasing current on the one to the right, and we're increasing current on the left. You can see how they make contact here. Now, they come in and make contact from the ends, and we'll show you what that looks like too, just so you understand how beautiful these things can look when you found them. Look at these we found worn out. Many of these passed simple volume tests at the Schrader valve. We're going to show you how to find these. Let me put this in perspective for you. A simple thing like looking at the current flow on all fuel pumps for vehicles with over 100,000 miles that come into your shop yields some surprising results. People who've done this, and we've encouraged them to do it, tell us they're selling 1, 2, 3, maybe 4 extra fuel pumps a month. They're finding fuel pumps before they leave the customer stranded on the highway. Let me say that again. They're selling fuel pumps before they leave the customer stranded on the highway. That's an important finding. Look at these dark areas over here in this one. That's where the brushes have not even been making contact. You can see on the other side, they've been making pretty good contact. But remember, it takes 2 brushes making full contact in order for this to work. Well, how do we test this current flow? We've taken a circuit here and highlighted it in red. And people say, well, okay, that red area is a really ideal place to go measure fuel tank pressure. Great. What makes this the best area to check fuel pump? Why not just go to the fuse up there? It's in a fuse box. It's easy to get to. Well, it's a 15 amp fuse. Now, this diagram from the manufacturer says it's just going to one place and one place only, and that's to the fuel pump. But unfortunately, we don't need a 15 amp fuse for a fuel pump. It's got to be powering up other things. So we've highlighted this in red saying, hey, pay attention. If you're not sure that all the current at this fuse is related strictly to the fuel pump, go into the area like this in the red area. We can show you some other areas that make this simple. It might be easier if you remove the fuel pump relay and place a loop of wire in here. What do we need to do to power up this fuel pump? Let's look at that connector at the top. We take the battery plus at the top left. We plug our one lead in there, make a loop of wire, plug it into the fuel pump. We have now plugged it directly to the fuel pump without the relay. This is a good way to verify when you have a bad relay or a relay that's not functioning. If you do this and the vehicle suddenly runs, congratulations, you've solved the problem. But what this is doing is powering the system up directly from the battery. So be careful. This battery plus is battery plus because it's always hot. But we are now able to go right here and absolutely positively measure the current flow at the fuel pump or going to the fuel pump at this spot. We're going to hook our low amps probe around the loop of wire and go get a scope pattern. Now, we can also go down and find an easier location if you want to. Here's one we found in the trunk by removing an access plate. We can go do it there easy enough. We can either use power or ground. Remember, this is polarity sensitive. If it looks like the pattern is upside down, just turn it over. But let's say something. The first thing we're going to do is we're going to measure the average current. Look at the size of this scale. This is a 10 amp scale. Okay, and we have a specification here for this particular vehicle. where it needs to be between 4 to 8 amps. Really, we're looking for something around 6 amps, right? Let's measure it. We're just under 5, right at 5, right about 5. What does that tell us? Yeah, we're toward the low end of the scale, but we're not at the bottom. We probably have sufficient flow from this fuel pump. And the irregularity of the pattern tells us a similar thing. What are we looking for then? Well, take a look at this particular one here. Here's another vehicle, same specs. The average current is down around 3. We said we're looking for around 6 nominally. Last time we're at 5. Now we're under 4, close to 3. We are 40 to 50% below the volume capacity of this pump to one that has 6 amps. The amperage is directly related to the capacity. We can't get full output unless we get full current flow to it. We can't get good current flow if we've got dirty, worn commutator rings, worn brushes on the motor. The only reason this current is low, if we have B+ and ground at the pump, is because the brushes have wear. How hard is it to test? It's going to take us 2 minutes. What's the payback? Really good. What does it find? Unusual problems? Yes. It finds problems we can't find other ways. Now, you see all those ripples in the pumps. Those little ripples are the brushes going from commutator ring to commutator ring as it rotates around. We can even get down to doing things like looking at how much ripple we have here. The height of this ripple tells us how hard the pump is working. If it's almost flat, it ain't really pumping. It's just spinning. Let me say that again. If it's almost flat, not a very big ripple, it's not working very hard. It's called cavitation. It means it's pumping. We've lost the ability for the impeller to compress the liquid. It's not really doing what it should be doing. If they're too high, we probably have a dirty fuel filter or some other restrictions because the pump is working very hard. When it works hard, current flow goes up and the ripple current goes up. We don't want to see the ripple exceed 15% of the average current draw. The average current draw here is 4.6 amps, so you can figure out what 15% of that is. But there's more information to be determined here. Check for large dropouts. Now, even though this pump amperage is too low, there are no dropouts. Now, we've seen new pumps that look a little irregular. That's why we're saying look for dropouts. We want to see something bigger than just minor things. Now, don't ever expect to see one this bad. But here is a very unreliable pump with excessive dropouts. This is the classic pump you hear about, that you start the car, drive it, stop it, and then it won't start. The reason it won't start, it stops on down in one of these dead spots, and it's stuck there. Any little vibration or something might make it make contact, and then the car starts. This is a pump that is going to leave the customer stranded. Please don't wait till they get this bad before you replace them. When the dropouts go to getting pretty good size, be aware of them. But be aware until the brushes break in. There is some pretty big irregularities in brand new pumps. So let's talk about something else we got to look at. Since we're measuring current flow, we've got to be aware of duty cycle controlled fuel pumps. Their patterns will be uneven naturally. You'll know it by looking at the schematic, and it says fuel pump driver modules. This is a variable speed pump. You have a duty cycle where we're controlling fuel pressure. This is particularly used on your returnless fuel systems because we regulate the fuel pressure by regulating the fuel pump. Its duty cycle will change fuel pressure. This is what a pattern looks like. Now, yeah, you say this looks a lot bigger. This is on a 5.2 amp scale. We scaled it down to make it show up bigger. If this were not a duty cycle pump, well, you know it's a duty cycle pump. How do I know it's a duty cycle pump? You say, how do I know it's not a dropout? Well, look, I see 1, 2, 3, 4, 5, 6. I see 6 or 7 pulses on the way down into those dropout times. Those are partial revolutions of the motor. What I'm looking at here is about a 1 or 2 revolutions of the motor is what this dropout is. It can't be a bad commutator because there's a whole bunch of commutator contacts in that pattern. Make it simple, stupid. Look, there's a lot of little pulses in there. Those are different commutator rings. It's not a dropout. It's duty cycle control. Now, let's talk about commutators. Most are 8. We've got a few cheapos that are 6. They're usually aftermarket replacements, and they're pretty bad. Some of the larger trucks and stuff have 10 segments. You say, why would I care about that? Well, we want to identify it, and we want to talk about that. We're going to try to identify unique things about a pattern in order to figure out how many commutators segments we have. How many little bars are there in the commutator? Now, we've got one segment picked out here. Look at it very closely. It's slightly taller than the others. Look to the right. Is there any other that are slightly taller? How about right there? And right there. Wow. Where the dotted lines start is 1, 2, 3, 4, 5, 6, 7. The arrow is on 8. Starting at the arrow, 1, 2, 3, 4, 5, 6, 7. Where the arrow is, we're on 8. This is an 8-segment commutator. And if you look, every 8 spaces, it's a little bit taller. Yes, you have to pay attention. Well, what are we going to do with this? Well, those 8 segments means we have made 1 revolution of the motor. Oh, 1 revolution. We measure the time. In 1 revolution, we've used 9.12 milliseconds. 1 revolution took 9.12 milliseconds. Okay. RPM is simply milliseconds, 60,000 of them, divided by 9.2. Okay. 9.2 is the time for 1 rotation. So let's divide that into 60,000 milliseconds to see how many RPMs we have. The answer, 6,578 RPM. Oh, we can actually measure the speed of the fuel pump. We really want to see it stay above 3,500, 3,600 RPM. We get down to that kind of speed, it's getting pretty slow. Current flow is probably also going to be low. What are the symptoms that are going to point us to look at a test like this where we're looking for a low-speed pump with low amps? Remember back when we did the wide-open throttle, high rev, and we looked at long-term fuel trim? If long-term fuel trim is up around 10% at wide-open throttle, at higher revs, 2,500, 3,000, come look here. This is where you look for your low fuel delivery. If you happen to be lucky enough to have a newer vehicle that's got an air-fuel ratio sensor, a wideband air-fuel ratio, whatever you want to call it, and you can't get 13.2 or less, get a little richer in that range. If you can't hold 13.2, if it starts dropping back toward 14, come look here. This is tying the whole thing together. These are solutions you need to look for when you have those problems. So current flow and the low amps probe are the 2 most important things. If we've got low amps and we got low current, you have a low output fuel pump. If one or more things isn't correct, we get a little skittish. The pump current draw is near the minimum, we worry about it. Okay? If the difference is greater than 15%, why is the pump working so hard? We're not going to change it for that. And if it's between 3,400 and 10,000, well, the pump is probably spinning okay. We get around 3,400 RPM, we start worrying. If amps is below normal, we've got a definite finding we aren't making contact. What you're going to find when we have bad amperage is you're going to find yourself getting down, crowding that 3,400, 3,600 RPM range. Replace the pump if a combination of these fail. What's your confirmation? You had high long-term fuel trim at wide open throttle, could not supply full power. You had a wideband air-fuel ratio sensor. We couldn't hold a good 13.2 or somewhere in that range. It started creeping back toward 14 the longer we kept the throttle open. That's why you come here and look at this. So we came here for a reason, and this is verifying things we might not find with conventional test techniques. So that's what we're doing here. Now it's time to move. If we get the right pressure, we got the right volume, now we've got to deliver it to the cylinders. And just because pressure and volume are normal, that still doesn't get it to the cylinders. Injectors have to have normal electrical operation. They can't be partially shorted. They also can't be dirty and gummed up. Now, normal electrical activity may not deliver the proper fuel charge. Electrically, it may draw the right amperage, the voltage is fine, the ground is fine, but if the injectors are dirty and clogged, they won't deliver the proper fuel flow. We can look at different testing. We can look at voltage testing, and we'll talk about that. We can also look at current testing. We'll do current testing where the injector is turned on down there at the bottom. Hard to do? Well, it takes time. You have to come in and open the harness up and separate the wires at the injector like we've done here. Need a razor knife to open up that sheath so we can get in there, pull those injectors wires off to make a big enough loop. Now, what are we going to test? We're going to test amperage. That's the red low amps probe. On the other side, we're going to look at the voltage waveform. Now, guess what, guys? We're no geniuses. Most of the time, the amperage wire, the B plus wire, is pink. And all the time, the individual sequential injectors all have different color wires for the voltage waveform. We're not piercing. We're using one to slide down inside here beside this and not damage it so we don't make holes in the wiring harness. We're going to come here. There's our black and white wire, and that says black and white wire is going to that injector right there. So there, we look at injector number 5. There's our wire. That's where we go for voltage testing. The pink wire, that's where we do the current testing. There's our black wire. There's our signal. Let's go through and talk about it. I don't think there's anything new here. We're going to have normal B+. Why do we have B+? Because most injectors, except for a few Chryslers and other oddballs, are ground-enabled injectors. That means we supply ground to turn current flow on. When we turn current flow on, the voltage drops down near ground voltage. It's going to be somewhere near 0.2 volts. We're going to show you that, measure it, so you can see it. It's going to be on. That's the injector on time, the length of time it's on. And when it turns off, boom, we get an injector kick. Now, this kick should be the same on all injectors. If it isn't the same, check B+ and grounds. If they're normal, replace the injector because it's probably bad. There's something wrong with it if it can't get normal kick. And they'll all kick the same thing. When we're all done, it should come back down to battery voltage again. And there's nothing much to test out there. Let's look at an actual waveform we captured. Top up there, we're about 54 volts. They should all be about 54 volts. Now look at the bottom arrow. It says we're running 0.293 volts or 293 millivolts. 4.2 milliseconds injector on time. We can look at it. What does that 293 millivolts tells us? Tells us we're getting good grounds. Remember, this ground has to come from the computer. The computer supplying this ground. If you've got bad grounds at the computer, it won't be 293 millivolts. It'll be higher. See, we're going to turn it on right here. All of these solenoids are switches or electronic switches. They're going to close and supply ground to the right-hand side of these injectors. Now, the current is a little bit different. It can uncover problems that may not be detected by your regular voltage testing and resistance. Dynamic testing at full current uncovers resistance problems that may not show up doing ohm meter testing. We've seen it more than once. The pendulum movement. If we turn on a magnetic coil, which is what we've got in there, and the pendule, the piece in the middle, moves to the center, which is what it does in order to open the injector, it's going to cause a change in the magnetic field, which will cause a change in the current waveform. Oh, really? Well, let's look at it. Starting back at the basics, here's where we turn our current on. At the top is an injector going up to 1 amp. At the bottom is our voltage pattern we just did before. Here's where current turns off. Remember, that caused the spike, and this says current turned off. Bingo. We can see the same thing. Now, let's look a little closer at that current waveform. We're going to get over here on the left. We can get a number of injectors depending on where we get. We could collect them all if we connect to a common source to splice 124 there, where they all come to, or we can go look at them one at a time. When we look at the voltage side on the right, we have to go look at them one at a time because each injector is separate. There are no common places there. Here's how we're going to connect our probe. And remember, if we get it around the wire backwards, we'll just flip it over and turn it the other direction. One thing to remember, it's got a little button on there you push to zero it. This is not zeroed. The arrow on the left is pointing to 0, and the pattern is way below 0. Just to make it calibrated, zero it when you're ready to start testing, and then connect it up. Now, if you happen to accidentally put it on upside down, you'll notice the pattern goes off the screen like this. Be careful, it might not trigger, depending on how you have your triggering set up on your scope. So be careful what you're doing. If you think you got it wrong, flip it over, turn the other direction. What are you expecting? Well, we went and found a specification here for a 3.1 Malibu. It said the amp should be between 0.9 and 1.1 volts. 0.9 and 1.1 amps. It's 11.8 to 12.6 ohms. So we have both of them there. What are we reading here? We're reading on a 2 amp scale, and here is our peak amps. They're right at 1 amp. What does that mean? It means the resistance, the dynamic resistance, is just what we expect on this injector. The pendulum hump, we're pointing to it right here. This current changes when the pendulum, which is a magnetic core, moves. It moves in order to open the injector. It's being drawn into the center of the coil. This movement causes a change in the magnetic field, and we've already determined that changes in magnetic field change voltage. Now, you won't always see these beautiful clean ones like this. Sometimes they're going to be more muddled like this. They're not all going to be bright, pretty, and pristine. But occasionally, you're going to see a sticking injector where it may not have any hump at all. How would we verify this lean condition? We're going to go back to our injector patterns. We're going to look at our long-term fuel trim. Remember, we don't have to rely on just one test here. These tests, like this, are using this type of information to pinpoint why we have determined we have lean condition on a cylinder. We've seen it in the injector waveform. And what's surprising is it's not going to be as lean as you think it is when you have a completely stopped injector, if it's just one injector, because the whole intake gets charged each time an injector. It's shared fuel, scavenger's fuel, for some other cylinders. So take it off idle in order to see the secondary waveform show this problem right here. This is why we like to see it under 5. Injector that's not doing the right thing, we can have problems. We can use voltages to find bad injectors that cause lean conditions, that verify things we saw in long-term fuel trim. The current can find injectors that may not show up in other situations. We can see if the pendle's moving. If it's not moving, it's probably stuck. A stuck pendle is usually very dirty and leaning the fuel mixture out. Go back to our fuel trim, our injector patterns, to all verify these conditions, to bring us here to look at this. We don't have to look at every vehicle we work on for this. Why? Because we've already gone through the easy stuff with fuel trim and everything else. If they're fine, we don't worry about this. It's taking care of itself. We come here when we're directed to go here. Now let's talk about the other causes of misfires, things you're not going to see. Mechanical engine conditions. Valve sealing that's not working right. We told you to watch your secondary patterns, that causes a lot of turbulence. So will head gaskets do the same type of thing. Crank and cam misalignment because of worn timing belts, slip timing belts, whatever the case may be. Look at the relationship. Do the cam and crank signals line up on your scope the way they're supposed to? And don't overlook vacuum leaks. They can lie to the computer about the amount of air entering the engine. Restricted exhaust can sneak up on you and say, why can't I get any power? Why can't I get any air into this engine? Maybe it's because it can't get any exhaust. And don't forget strange things like the fuel composition sensor on flex fuel vehicles telling you you've got unusual amounts of alcohol when you don't, because that's going to change air-fuel ratio. Do your mechanical compression testing. Please check manifold vacuum. Look at it. Is it a steady throttle? Does it have a tick? Use your smoke machine to find vacuum leaks and other things. Do back pressure testing. There's adapters you can screw into where the O2 sensor is to measure the back pressure. The instructions come with it, tell you a very easy test, works great. And we like vacuum transducer waveforms on the scope, but we're not trying to make this super advanced. We're trying to make this super detailed. We didn't get into some of the tricky, interesting stuff we find that we could be doing. So in summary, verify the stuff in mode 1, your parameter IDs. Check all your trouble codes. Live by freeze frame, and that's what you need to drive when you go back and test for repair. Learn more about mode 6 if you don't know it. If you know it, please use it. Verify the computer inputs, then verify fuel delivery, then identify individual problems with the ignition system. Look how easy it is. If the inputs are normal and fuel delivery is normal, we don't bother with the ignition system unless we've got a code sending us there. When we get there, it says, hey, there's something wrong with cylinder X. Now we go into our detailed study. We go back to our computer inputs. Can we get full fuel delivery? We're going down the highway when we need it. Tie all this together because these are not a bunch of individual tests. These all tie together, and when you learn to do that, you'll become a super technician. Hey, this is Bill Peak. I hope this helps you. Doc and I have worked hard on this program to try to give you a comprehensive overview of all the things you need to be looking at when you're looking at fuel control and misfire problems. Good luck, and I hope this really helps you do better.